So today we have Kevin Leyton-Brown with us from UBC. Lance, you're not paying attention.
He's met me before, it's okay.
You said today we have Kevin Leyton-Brown from UBC.
You're distracting the other audience members. Do not talk in my class.
Talk when and if I want to.
Kevin's an associate professor now at UBC. He had spent time in Uganda for the first half of his sabbatical, working on very fascinating problems with the Ugandan police in more ways than one. And, then he went to Israel for the algorithmic game theory semester at Hebrew University with me, and today he's going to talk to us about beyond equilibrium.
Thanks. So yeah, the thing that I'll be speaking about today is joint work with my PhD student James Wright, who of course did all the hard work, but I'll be happy to take credit for it. So here's the context of what I'd like to talk about today. So I guess, how many people in the audience here kind of work on game theory on a regular basis, just to know who I'm talking to? And how many of the rest of you hear about game theory more often than you wish you did? So this is another one of those days. So game theory studies how people will behave in a kind of idealized strategic situation where the notion of behavior kind of comes from what John von Neumann was thinking about in the 40s, that you know, given your utility function, you're going to do kind of exactly the right rational thing. And we all kind of understand that this is not really what people do. But the interesting thing is that what people do is actually pretty reliable and repeatable. So the question that I got interested in is, you know, what can we say in terms of a formal model about what people actually do in game theoretic situations? So I started to look at the kind of simplest version of this problem, because it's always good to start with a simple problem before you scale up and make it more complicated. So I thought about what people call initial play, really unrepeated games that are both simultaneous move and two-player. So essentially playing a normal form game against somebody else once. And I'm not here requiring that the game have two actions, some arbitrary number of actions in an unrepeated game. So there's this whole branch of economics called behavioral game theory that seeks to extend game theory to talking about how actual people play games. And this literature has proposed all kinds of different models that seek to make this kind of prediction. And so what I wanted to do was kind of go to this literature and figure out what are the good models, so that I can then take the good ones and then start to prove something about them, or look at how I could extend them, or something like that. And what I found actually really surprised me, which is that there were, first of all, this behavioral game theory literature hasn't been really all that concerned with predicting how people would play games, which it seems to me when you have a theory, you want to show that it's a good theory by showing that it predicts new phenomena. But the other thing you can try to do with a theory is to show that it explains the phenomena that you've already seen. And it turns essentially that it compresses the data that you already know about, rather than extending to new data. And this kind of compression story has been pretty much what the behavioral game theory literature has looked at. So I wasn't able to look at the literature and know which model is the most predictive. Furthermore, I also wasn't really able to go to the literature and know which model is the best among all of the models. There really hadn't been much of a study about just comparing the different models to each other. Pretty much what people had done was take their own models, compare them to Nash, show that Nash did a terrible job of showing how people behave, which is probably not a big surprise to any of you, and then asking sort of how can I configure my model to make it as good as possible at explaining the data. So this isn't really what I set out to do, but in the end, I found myself just trying to make sense of this literature so that I could figure out what is the best behavioral game theory model in terms of its predictive behavior. So that's sort of the hook that led me into this. So what I ended up doing was looking at all of the different models that have been introduced in the behavioral game theory literature and asking about them which is the most predictive? That'll be kind of the first half of my talk, is answering that question. And what we found is something pretty surprising for this kind of statistical approach. We found that really there was one model that was the most predictive in a pretty consistent way. When you do experimental work, it's not always the case that you get a clean answer out, but this time we really did. And so we then sort of turned to sensitivity analysis kinds of approaches to ask, how can we better understand this model that we found to be the most predictive? So I'm going to begin today by just telling you about these different models so that you kind of know this lay of the land. And to do that, I want to motivate by thinking about an existing game. So how many people here are familiar with the Traveler's Dilemma game? Not very many of you. So here's how the Traveler's Dilemma game works. You and a partner are asked to pick a number between 2 and 100 simultaneously. Now, if you both pick the same number, then you both get that number as your payoff. So think of these numbers as amounts of money. So if you both pick 100, you both get $100. If you both pick 17, you both get $17. If you pick different numbers, then you both get the lower of the two numbers. And additionally, there's kind of a transfer. The person who picks the higher number has to transfer 2 to the person who picked the lower number. So the kind of intuition here is that if you're greedy and you pick a higher number than the other person, then first of all, you get the lower number, and secondly, you kind of pay a penalty to the less greedy person of 2. So, okay. So I guess you guys all seem a little bit sleepy. I realize you're eating some kind of high carbohydrate food here. So to wake you up, let me give you just a minute or two to play this game with each other. Because what I really want you to think about throughout this talk is how actual people would play games when they know they're playing games against actual people. And you look like actual people to me. So I think you should try to play this game with each other. So you can play as many times as you want, but only play once against the same opponent. Because I don't want you to be thinking about how you would adapt to what you've seen somebody else do. And just, think about these in terms of actual amounts of money between $2 and $100, and do whatever you think will make you the most money.
Do what?
What?
No, you have to pick a person on.
Are you trying to play with me? First of all, 1 is not an option because it goes to 2. So you've misunderstood the action space. This has the advantage that I can get another bite of my sandwich.
So stupid. Maddie, you used to play with the I'll play with you.
Excellent.
You should say 99. Alright. That's what makes me living fun. Yes. Choose one. Is there
Okay, I heard the number behind.
Oh yeah, pay 101 if I chose 99. So he gets 97.
But you know what I said about 100?
All right, so let's wrap that up. So let me just kind of see a kind of cumulative density function of what different numbers that you all called out. So I'm going to say numbers, and I want you to put up your hand if the number that I say is less than or equal to the number that you played.
Wait, less than equal.
So in other words, I'm going to say descending numbers, and once your hand is up, it's going to have to stay up, because it's always going to be the case that my number is less than or equal to everything once you go up, right? So who played 100? 99? No, you see, you have to stay up, Lance, because we're doing a cumulative density function. So you weren't paying enough attention. You were thinking about your blog. Okay, 99, 98, 97, 96, 95, 92, 90, 85, 80, 70, 60, 50, 40, 30, 20, 10, 3, 2. All right. So here's the thing about this game. This game has a unique Nash equilibrium, as I imagine most of you can see. And this is a Nash equilibrium in a pretty strong sense. It's the unique strategy that survives iterative removal of dominated strategies. So you can reason as follows. Let me consider playing the strategy 100, as most of you did. This is a terrible idea, because the strategy 100 is not a best response to anything, right? If I was to play, let me consider everything that I could play 100 against, and think about the alternative of playing 99 instead. And against anything less than 99, they both amount to exactly the same thing. I get the same payoff either way. Against 99, I'm better off playing 99 than playing 100, because I would get a payoff of 99 rather than getting 98. And against 100, I'm again better off playing 99, because I would get 101 instead of 100. So clearly we can reason no agent would ever play 100, because that would be ridiculous. And so I can be so sure that no one would ever play 100 that I can just take it out of the strategy space completely. And I can then say we have a game that goes from 2 to 99, and then I can apply that same reasoning to 99 and say, really, 98, having eliminated 100, 99 is now dominated by 98, and so I can throw out 99, and I can keep doing this until I get nothing but 2. And so 2 is the unique Nash equilibrium of the game. Yeah?
Does it argument apply to mixed strategies?
Yes. Yeah, so this means that there's, because you would never mix over something dominated. So this is the unique equilibrium of the game. It's pure. It's identifiable just by iterative removal of dominated strategies. So a game theorist would say, you know, I can make a stronger prediction in this game than I can in a kind of arbitrary game where equilibrium selection would be an issue and mixing would be an issue. Here, there's a pretty simple story, except, as you can see, this story didn't do a very good job of describing what you all did. It described very few of you, and I would claim that those of you who played 2 out of a sense of loyalty to game theory rather than a sense that this was actually a good way to make money.
I think it was a sense of spite for our opponents.
That's also possible. So, but here's the thing. People do something pretty reliable when they play Traveler's Dilemma. The vast majority of human players choose 97 to 100. I put this on the slide before I got to see what you were all going to do, and you bore out my prediction. And isn't that kind of interesting, that people do something predictable that's just not the thing that game theory says that they're going to do?
I don't find this a very interesting example, because
No? Why not?
if I do 100, I get within 2 of optimal,
Right.
of what I could optimally do, and 2 is very small compared to 100.
And
Or if I play 2, I could really hurt how much money I make. So if
That's
I'm
true, but
conservative
basically
kind of guy, I would want to play 100.
Right, but that I think I completely agree. That's
So I don't find, in fact, this bears out exactly when you see what, when the company's much larger, you're going to be close to Nash equilibrium, because then you're risking more money by spending 100.
So that's all fine, except that the models that we turn to that tell us what should happen in a game don't do that kind of reasoning. So, I mean, that's a minimax regret kind of argument that you're making.
And epsilon kind of equilibrium.
Well, I mean, $2 is a pretty big epsilon, right? This isn't a kind of argument that works as we scale epsilon down. And I argue, I think that's a very reasonable way to think. I think that is the kind of way that we think. But that's really, like, you're throwing out Nash equilibrium if you want to make an argument like that. That's going to take you to a very different part of the space than Nash equilibrium, which is fine, but I think it tells you...
Well, I mean, we deal with the epsilon Nash equilibrium quite a bit.
Well, but I think, anything is going to be an epsilon Nash equilibrium. I don't think you're going to get to a case where 100 is the unique epsilon Nash equilibrium. I challenge you to think of a model that predicts what you did, that's derived from Nash equilibrium. I don't think you're going to be able to do it.
But this also assumes that people really trying to maximize their payoff. But there's a model that assumes people are trying to maximize the max mean function or something like that. That's going to predict the 100.
I guess it doesn't assume anything. What I'm trying to point out is that there's a kind of orthodoxy in game theory that says Nash equilibrium is what will happen in in a system involving rational agents. And in fact, this is sometimes true. I mean, this is an example in which Nash equilibrium does badly, but sometimes it does well. This is just meant to point out that game theory sometimes does catastrophically badly, or at least kind of standard game theoretic solution concepts sometimes do catastrophically badly at predicting how people behave. And you guys can then sort of propose other things that might do a better job of explaining what people did here. And I think, in fact, that you can come up with several different things. My point is just it's not Nash equilibrium, right? We're going to have to start thinking about other models. And particularly for the traveler's dilemma, I don't think it's all that hard to come up with a variety of different models that would work for the traveler's dilemma. I'd like something that's general, that really is a function that, given any game, will give me a prediction of what you're going to do that's going to be reliable across games. So it's also kind of difficult to, if you make an epsilon story, what exactly should epsilon be? How should you really think about what the size of epsilon is that people care about? Is it really max-min? Sometimes Nash works pretty well. But this is really the question. How can we start coming up with a model that describes what we just saw, but that would work on general games? So that's the thing that I want to talk about. So in the literature, there are two kinds. Let me just really emphasize, I really want to find things that are mappings of this kind. So that are going to be able to take an arbitrary game as the input and give me back a probability distribution over actions in the action space of that game as the output. So anything that's kind of a rule of thumb that would apply to a game with a particular kind of structure isn't going to be kind of admissible to me here. I want to find something that would work on any game. And there's a literature that aims to do that sort of thing. There are basically two kind of key themes in that literature. The first is called Quantal response. And this idea says that people play best responses only with high probability rather than all the time. So if I have three actions, one of which is going to give me the best expected utility given whatever you're doing, one of which is going to give me almost as much expected utility but less, and a third that's going to give me very little expected utility. This says I would play the first and the second almost with the same probability, and the third I would still play but not very often. And that's what this idea is. The second thing, called iterative strategic reasoning, says that I don't really do arbitrary amounts of look ahead when I'm reasoning about the game. So Nash equilibrium says that I'm going to kind of do backward induction sort of as far into the tree as I want. And we're going to kind of find the fixed point of this sort of common knowledge of rationality. This says I do kind of look ahead in the game, but I don't look ahead arbitrarily deep. And maybe that's because I'm not capable of it, or maybe it's because I don't believe that you're going to be doing it, and so I don't think there's a value in doing it any further than you're going to do it. So there are different models that combine these ideas in different ways. The first is called Quantal response equilibrium. And the idea here is that everybody's quantally best responding to each other. So formally, I can define a quantal best response in the following way. So I take this logit. I say I have a parameter lambda, which is kind of a magic number. And I know the mixed strategy that everyone else is playing, S minus I. And I say, what's the probability that I'm going to play action AI? Well, I take e to the power of lambda multiplied by my utility for playing AI, given the action of everybody else. And I normalize that by the same thing for all of the other actions that I could take. And that's the probability that I'm going to assign to playing action AI in my mixed strategy. So this all depends on this kind of magic lambda. Let's think about what this means for different lambdas. So if lambda is 0, then this is going to amount just to uniformly randomizing over all of my actions. And as lambda grows, it's going to approach a best response, because the differences between very small utilities are still going to be magnified, and they're still going to end up swamping anything but the biggest utility. So we have this kind of parameter to worry about, but this is a kind of best response notion that kind of scales between uniform randomization and real best response. And a quantal response equilibrium is everybody quantally best responding to each other. It turns out that there always exists such an equilibrium, and it's unique for any given parameter.
A question?
Yeah.
Does it assume that everyone has the same lambda?
Yes, and the equilibrium notion does. Okay, so the second idea, this iterative strategic reasoning, says, let me kind of think of every agent as having a level, sort of like a type of the agent. A level 0 agent we're just going to define as somebody who uniformly randomizes over the action choices. then a level 1 agent is somebody who reasons about level 0 agents. And a level 2 agent is somebody who reasons about level 1 agents, and so on. And I'm going to be given a probability distribution over levels in the population with kind of the intuition that higher level agents are sort of smarter and scarcer in the population. I'm going to have some kind of tailing off distribution over the levels. And then remember, what I really want is something that, given an arbitrary game, gives me a distribution over the actions. So the way to do this is that I make a weighted sum of the distributions for each level. So I make a prediction for what each level would do, and then I just weight them by their relative likelihood. So there are two models that incorporate this idea. The first is this level K model due to Costa Gomez et al. It has 4 parameters. These parameters are going to be important in what follows, so I'm just kind of calling out the existence of these parameters. In this model, we say every agent has exactly one of 3 levels, so level 0, 1, or 2. And we have kind of a histogram distribution over these 3 levels. So I have a parameter for how many agents are of type 2, how many are of type 1, and then the remaining probability masses for the agents of type 0. And I also say that each level K agent makes a mistake with an error probability that depends on their level. So I have 2 parameters for error probabilities. The level 0 agents don't make errors because they're already uniformly randomizing, so there's sort of nothing else for them to do. And an agent of type K believes that all of his opponents are of type K-1 and don't make any errors. So level 2 agents are best responding to what level 1 agents would do, and so on. A different model that also makes this kind of, yeah.
Sorry, I just want to make sure I got
Please,
that.
yeah.
Level 2 is responding to level 1, assuming level 1 doesn't make mistakes?
That's right.
Okay.
So you could imagine setting it up assuming that they do make mistakes. This is just the way it's proposed in the literature. So this other idea called cognitive hierarchy has 1 parameter. And this says, let's have a little bit less kind of false beliefs than we have in the level K model. Let's say that everyone best responds to the truncated true distribution of levels below themselves. So kind of the intuition is you wouldn't want to be level 2 if you think there are level 3 people in the world. You would want to then be kind of level 4 so you get the jump on them. So you should kind of believe that everyone is sort of under you. But you should believe that there are multiple different ways of being under you. So here we assume that the levels have a Poisson distribution, which has a single parameter that describes it. And then everyone best responds to the true distribution of types underneath them. And finally, there's one more model I want to tell you about called Quantal level K. This is the earliest model proposed in the literature. It's from '94, and it has this kind of messy 5 different parameters. It basically works the same way as level K, in that we have this histogram distribution over the 3 different levels. But rather than saying people best respond to the level beneath them, it says people quantally best respond to the level beneath them. So they do this logic quantal best response function that I showed you. And they do something very complicated with these lambdas, the quantal response parameters. So they say each level has its own lambda. So the level 2 agents have the quantal response parameter lambda 2, kind of responding to what you asked before. The level 1 guys have lambda 1. And the level 2 guys have to respond to the level 1 guys, which means they have to have a belief about what lambda 1 is. And this model says that belief might be wrong. That might be different from the true belief. So we have a 5th parameter, which is the belief that the level 2 guys have about the level 1 guys parameter. Seems complicated, but I didn't make this up. A bunch of people who do experiments with people thought this was the right model to have, and it's discussed in the literature. So this is what QLK says.
So in the original, the first one you choose here. So if I'm a level 3 guy, I think everybody else is level 2. So level 2 guys I know are defined that they respond to level 1 guys, but I don't think there are any level 1 guys in this game. So what does a level 2 guy
so a level 2 guy just has a particular probability distribution over actions. You kind of think, these guys are idiots for thinking there are any level 1 guys in the world, but whatever, that gives them a particular distribution over actions, and that's what I'm going to quantally respond to.
Okay.
So unlike game theory, these theories end up with a lot of wrong beliefs in them. As I guess, your play of Traveler's Dilemma did, right? After Traveler's Dilemma, one person would think, oh, I really did the wrong thing. I should have changed and done something else. So, unlike an equilibrium notion where everyone really has correct beliefs, here you're going to have people with wrong beliefs. Okay, so I'd also like to make predictions using Nash equilibrium, so I can compare to Nash equilibrium. This turns out to be annoyingly hard to do for 2 reasons. first of all, games often have multiple Nash equilibria. And when a game has multiple Nash equilibria, it's not clear how I should use this predictively to say, here's what I think is going to happen in the game. I have to make some kind of decision about equilibrium selection. Secondly, Nash equilibria sometimes assign probability 0 to some actions, as in Traveler's Dilemma. And in those cases, I can kind of have a problem with the way that I'm going to end up scoring these different predictive methods. That if a method says this thing will never happen, and then you observe it, you've basically refuted that predictor, right? You've said, well, I don't need to see anything more. One example where something that a method says is impossible is sufficient to refute that thing. And that would be a pretty lame way for me just to say, once I saw somebody do something that wasn't in Nash equilibrium, so let's never think about Nash again. I want something that's a little bit more reliable to still allow me to talk about Nash. So I want something that it isn't going to allow it to kind of get refuted. And so I'm going to end up proposing 3 different kind of Nash-derived models here. The first one is something I could really use for prediction. So I'm going to say there's some error probability that you're going to uniformly randomize rather than playing Nash. So I'm going to have a parameter here as well. And that's to ensure that it doesn't get refuted. And then I'm going to otherwise predict a randomly chosen Nash equilibrium. So I'm going to randomize over the different equilibria as a way of solving the equilibrium selection problem. Now, but maybe there's something special about the equilibrium that people realize and I don't, and maybe the best Nash equilibrium does a lot better than the randomly chosen one. So another thing I can do is to kind of pick the post hoc best Nash equilibrium, non-deterministically. So this is not something I can do for prediction, but it's something I can do to kind of bound how good it's possible to do with Nash. And again, I'll also allow myself error here. And I can also do the same for the worst Nash equilibrium, just to kind of get a range on what Nash equilibrium predictions look like. So now let me tell you something about how I would evaluate these kinds of models, how I would use them in practice. So naively, when you first think about this for 5 minutes, it might seem to you that the right thing to do is to kind of count how often a model is right or wrong. But in fact, you really can't do this, because all of these models are predicting probability distributions over actions, and you're observing instances of play. So you can never really tell what distribution somebody had in their head. All you see is different actions that got played. So, and furthermore, I could have a model like everybody uniformly randomizes all the time. That could be my model. You're never going to see any play that will be inconsistent with my model. So if you want to decide that one model is better than another, it has to be because the distributions that it predicts make the data seem more plausible than another model, not because there's some kind of correctness about the distribution. So the right way to formalize this is to say that I want the model that maximizes the probability of the data that I've observed given its parameters. So I want the maximum likelihood model. And because I want to think about prediction, I want a model that maximizes the probability of data that I didn't use for anything except evaluating this probability. So in particular, I've got these parameters that I've got to set somehow in the model, and that might make a really big difference. And I don't want somebody to say, well, you just picked the wrong parameters. This was a really good model, but you set the parameters wrong. So to set the parameters properly, what I want to do is to take one set of data and use that data to find the parameters that do the very best on that data, and then take a different set of data that's distributed in the same way, and look there at this likelihood probability. So this means that I've got a really annoying optimization problem to think about. I've got to do this non-convex continuous optimization problem to find these maximum likelihood parameters. This is something that in practice took us a lot of time to think about doing, but it's not very interesting to the message of the talk, so I'm not going to tell you about it. But this is kind of non-trivial to do. Now, to estimate generalization performance, where do these kind of test and training data sets come from? To get a statistically more reliable prediction, I use a 10-fold cross-validation, which means I do this split 10 different ways, and I average across the likelihood that I got in the different splits. And this has the problem that the estimate may still kind of depend on the way that I did the splitting. And so I also average across multiple ways of doing the splitting, and get a confidence interval on the result of this whole cross-validation run, which is kind of a standard thing to do. So if you're not a machine learning person, don't worry too much about this, and if you are, then this is what we did. So what data did I use? basically, I want to look at how actual people played games against each other in situations where they were really motivated with the right utility functions, which means they were paid actual money according to their performance in the game. And this kind of data is expensive and difficult to calculate, and expensive both in terms of kind of time and money, and requires a lot of skill to gather. So this is not something that I did myself. This is not my skill set. But luckily, many people over the years have done these kinds of experiments with human subjects, usually kind of psychology undergrads, and have published this data online. So what we did is we took all of the data of this kind that's publicly available, and we studied kind of all of it. Which I think is the first time that this has been done. So this is kind of a large meta-analysis of kind of everybody else's data. And in particular, we got here 9 different experimental studies, and then we also made one new data set of our own, which is just the same number of instances from each of these 9, each sampled at random from the different data sets. And this last one is kind of the one that I'm the most interested in because it's a really kind of general and heterogeneous data set that averages across everything that I know about. So it seems if you can find something that really does well on this data set, that's kind of the best I can say for something that would really do well in practice. So that's everything I have to tell you about how I set this thing up. Let me now actually tell you what we learned. So I'm going to show you a few graphs like this. So let me walk you through what this graph means before I start interpreting the results. So on the x-axis here, I'm showing you which data set I'm talking about. None of these data sets really mean anything to you, so don't worry about their identities, except for the one on the left, which is combo 9. That's the aggregate across all of the data sets, and that's the one I would argue is the most interesting. On the x-axis here, I'm plotting the likelihood improvement over uniform random sampling on a log scale. So let me explain what that means. So what I'm looking at, I compute in the way I described to you the likelihood of each individual model on test data, and then that gives me some number, right? It's going to be typically a very small number because anything is very unlikely when you're sampling. And then I'm going to divide that by the likelihood of my really stupid model that just says people uniformly randomize over everything. And you should think of that just kind of as a normalization. It just helps to put things into the same units. And so what these numbers mean is how many times more likely is the given model from the uniform random sampling. And if something was not any more likely than uniform random sampling, that should really worry you that it's not saying anything interesting. And this is on a log scale, so this point is 10 to the 30 times more likely. Now, the other thing to know about these kind of likelihood plots is that although it's tempting visually to do it, you can't make meaningful comparisons from one data set to another. Because the sort of overall magnitudes are really skewed by how many samples you have in the data set, how many actions there were in the data set, different things like that. So the relative heights here don't matter. It looks like, this guy's really small, but really that's just a small data set. But what you can do is make relative comparisons within a data set, because there you're making kind of an apples and apples comparison. So what you can say is, this thing is, 10 to the 5 times more likely than this thing, and that's a meaningful thing to say. So what can I then conclude? Well, I've got these 3 different red bars. The red bar in the middle is the actual Nash model that I could use for prediction, this randomization over Nash. This is my kind of non-deterministic best case for Nash, and this is my worst case for Nash. This is the best of the behavioral models that I saw, and this is the worst of the behavioral models that I saw. So right now I'm not drilling into the behavioral models and telling you what's what, but this is just sort of to tell you how does Nash do. And overall, if we compare the sort of medium red bar that we could actually really use to the behavioral models, you see there's a pretty big gap in almost all of the data sets. It's really never the case that Nash is doing phenomenally better than the behavioral models, and sometimes it's doing really quite a lot worse. So overall, this confirms what we kind of know from the behavioral literature, which is that Nash just doesn't do a great job at predicting how people behave in games. And this is even with this error parameter. I should mention that in all cases, to get even decent results from Nash, the error parameter is set really, really high. So when we do the maximum likelihood fit for the error parameter on Nash, we end up setting it to something between kind of 30 and 50%, which means this is not really what we would want Nash to be. It's not like I'm playing Nash. It's like I flip a coin, and if it comes up heads, I uniformly randomize, and if it comes up tails, I play Nash.
So
and that's
it shouldn't have a very high magnitude on this graph.
What shouldn't?
Because you're dividing by the uniformly random thing.
No, because then the other half the time the Nash prediction kicks in and matters. It's just that if I don't do that, the zero probabilities really penalize me. because they blow up the likelihood. So to sort of protect myself against the things that Nash gets wrong, I need to do this really high. But you're right. I mean, if I was to set that to 100, then it would be guaranteed to be 0. Okay, so now let me tell you about the behavioral models. So first of all, let me compare these two iterative strategic reasoning models to each other, the level K and cognitive hierarchy. And it seems as though these models are really different from each other. I mean, they have different kinds of beliefs. One of them has errors and one of them doesn't. One of them says there are only two different levels, 0, 1, and 2. The other one is Poisson, so it goes out to infinity. But in the end, when you tune their parameters on the data in the appropriate way, they end up doing almost exactly the same thing on every data set. Really, in terms of kind of statistical results, this is as close to exactly the same as you're ever going to see. So really what this seems to say is the differences between these models are not important. They both are able to capture really the same phenomena about how people think about games. Now, when I add in QRE, here you see that in some cases QRE is better. Here it's a bit better. Sometimes it's kind of a lot worse. Here it doesn't seem like there's a real ordering between QRE and level K. It seems like somehow they're capturing different phenomena. They just don't, there isn't one that you should prefer to the other. And this is the kind of thing that as an experimentalist you're worried that you're going to see, because there's just not a very nice story to be told here about the relative values of these two models. But then when we look at the QLK model, here we see that it just kind of wins across the board. And this is the model that really incorporates both of these different kind of design ideas, albeit with some extra complexity. And so, overall, on the big data set, it's really doing a lot better. And it almost always is winning. And in the case where it's not winning, like here, it's so close to tying that you might as well say it's pretty much winning. So it really seems like if you were going to pick one of these models, this is the model you should pick. And this is very embarrassing for the behavioral game theory literature, because this is the first model that was proposed in the literature. So this essentially says that for 15 years of literature after this model was proposed, people basically made things worse. But that's kind of surprising to me. But anyway,
by reducing the number of parameters a lot.
We'll get back to that. But there's not an inherent sort of value in reducing the number of parameters, because
I disagree, I think. I mean, it's an Occam's razor. You're trying to describe people's behavior. If you have a lot of parameters, it makes it, you're going to do a lot better describing people's behavior, but most likely you're not getting at the essence of why some of the people are doing things.
Well, so I guess I want to.
I think there are a lot of examples in economics where, like prospect theory, where you can explain lots and lots of things by throwing in a lot of extra parameters. So. But it loses a lot of its predictive power.
Fair enough. I guess I just want to point out that when you're testing generalization performance, as we're doing here, it's not obvious that adding parameters helps. Right? It's very often the case that as you add more parameters, generalization performance actually is reduced, which is actually why people talk about Occam's razor. The principle of Occam's razor is that actually, essentially, it's an informal way of thinking about the bias variance trade-off. Pardon me?
Like overfitting?
That's right, yeah. So generally speaking, as I add complexity to my model, it makes it easier for my model to fit noise in the data that I use to train the model, and it then can do worse at generalizing to data that it didn't actually see.
I was saying on a more, not a how well you fit model, but why do economists want things with small number of parameters?
I think it's a mixture of the two, but I grant you, all things being equal, if I had an equally predictive model, I would prefer one with fewer parameters, because it would be making a more definite prediction. Yeah?
You mentioned that training for those parameters was too complicated to talk about here. Was it not that much less complicated for the ones with slightly fewer parameters?
So, I mean, none of these models have all that many parameters, right? My worst model has 5 parameters. I guess my best model has 1, but my next best has 4. So it really, mostly we have sort of big-ish parameter space. I don't know. I don't think of sort of the constant 5 as being really all that big, but we're in sort of the same ballpark. But I guess it's nicer to have 1 parameter than to have 5. Yeah.
Well, we might get to this, but one of the parameters, if I understand, of some of these models is roughly guessing at how many levels deep people are thinking. I was wondering if you. Did that come out of this? I guess like a sort of a rough number.
Yeah, I am going to get into that. So and actually, indeed, I'm going to, although I was kind of disagreeing with Lance, I'm in the end going to more or less agree with the thing that he was saying. I mean, I think that I want to be clear that adding parameters doesn't mean that the model is necessarily going to do better. And in fact, we can kind of prove that in general, adding parameters at some point will hurt you in terms of generalization performance. But it's still the case that we would like to use these to kind of understand people. And the more parameters there are, sort of the less understanding I've captured because I've sort of externalized some of the things the model says. And for that reason, I'd like it to be simpler. Is there another question? Or no? So at this point, I can argue this QLK model really is the best model to use for prediction if you have to pick one of these models. But it's kind of a black box to me. It's got this complicated 5-parameter space. I'd like to now kind of understand what these parameters mean. So I'd like to ask myself kind of how strongly does the data that I looked at argue for particular parameter values? And what can I understand about people by looking at what this model does when I've set its parameters well? And so this is something I can't do using the methods that I talked about before, because this maximum likelihood approach that I told you about really ends up giving me a point estimate. It just says, here's a good parameter value that approximately maximizes this likelihood function. It doesn't tell me, actually, there were all kinds of other things that were pretty much the same, that were wildly different in terms of what parameters were good for them. And so if I really want to answer this question about how important the parameters are, I need to do something entirely different. I need to estimate the entire posterior distribution in the parameter space. So I need to, you can kind of think of it as a 5-dimensional response surface that says, for every configuration of parameters, what is the probability assigned to the data given those parameters? And I'd really like to look at that entire surface so that I can then start thinking about the parameters. There's really no other way to do it in a principled way. And this is what a Bayesian would do. And I can then think about individual parameters by marginalizing out all the other parameters and looking at kind of the density function in one parameter having marginalized everything else out. So the posterior tells me kind of everything I want to know. Now, as you would imagine, this posterior doesn't have an analytic representation. There's not some kind of clean way that I can get access to it. So instead, I need to use Markov chain Monte Carlo methods to approximately sample this space. And if I said before that the maximum likelihood estimation thing was kind of a black art that I wasn't going to tell you about, this really sucked to do. James spent 6 or 8 months just trying to get this working. There's a lot of nice theory about how Markov chain Monte Carlo methods work, but they're all in the limit. And it turns out the limit is really, really, really long, and you have no way of knowing whether you're in the limit. So sort of after the chain kind of bakes in far enough, it starts working, and you don't know whether it has. So you can do it, but it's kind of a black art. So in the end, we have a way of doing it, but I'm not going to tell you what it is, because again, it's not very interesting. But in the end, there's some statistical ways of verifying that what you have seems likely to really be the posterior, and in the end, we're pretty confident that we have something that looks a lot like the posterior. How am I doing on time? Do I go until 1, or do I stop a little bit earlier?
I teach at 1 after the appearance before 1. So
all right, I'm going to skip.
For me.
I'll say this part very quickly. So the Poisson cognitive hierarchy model has only 1 parameter. So it's not really the best of our models, but it's kind of a warm-up that I can think about here because it's a 1-dimensional space. And it has the advantage that in the literature, the author of the model made a very definite prediction about what this parameter should be. So he said, values of tau between 1 and 2 explain results for nearly 100 games, which gives you a sense of what they think big is in the behavioral game theory literature. Bear in mind, we're looking at 3,600 games in our big data set. And so he says, this suggests that a tau value of 1.5 could give reliable predictions for other games as well. So you might have some doubts about where this kind of analysis came from, but at least he comes out with a pretty concrete prediction, which nobody else really does. And so looking at this posterior here, I can show you the cumulative density function across parameters, which really here is the entire posterior because I have a 1-dimensional model. And you can see that, in fact, our 99% interval here is between 0.51 and 0.59. So basically, he was off by a factor of 3. And the density region is pretty small, so the probability that he would be right is actually vanishingly close to 0.
Is it a combo data set?
pardon me, this is on the combo
combo.
data set. We've looked also at all the other data sets, including his, and yeah, I mean, there's a bit of variation in them, but at best he's off by a factor of 2. So really, he's kind of horribly wrong. This gives you a sense, though, of how you can look at one of these things and sort of see what it predicts. And okay, so but I don't really want to know about this model that didn't work that well in my data. I want to know about this QLK model. So let me remind you what all of its parameters are, because I'm going to talk about its parameters here. So I've got these 2 different kind of histogram parameters that talk about the proportions of level 1 and level 2 agents. Then I've got these 3 precision parameters that talk about this Quantal best response precision. Remember this thing that goes between uniform randomizing and perfect best response for the level 1 agents, for the level 2 agents, and for the belief that the level 2 agents have about the level 1 agents. So computers chew away for CPU years worth of time, James works really hard, and then eventually this graph is produced. And so what does this tell me? Well, I've split out the distribution into 2 different graphs because they're kind of on 2 different scales. So this one is the probabilities, this is the alphas, the probabilities of the different levels, and this is the precisions. So what does this tell me? Well, there are a couple of things that are surprising about this picture. I mean, generally this is not a picture that looks the way that I want one of these pictures to look. And one thing that's really unhappy about it, you might not look at cumulative density functions for a living, so this might not jump out at you quite as much as it does at me, but these little stairs are kind of a bad sign. These means that there are many modes in the distribution. So the distribution is predicting, there's a bunch of density here, and then something else doesn't happen at all, and there's a bunch of density over here. And every time there's one of these stairs, there's one of those modes. So this is a really multimodal distribution, which is a messy kind of prediction to get. Furthermore, looking up at the alphas here, you can see that there are a lot more level 2 agents than level 1 agents, which is surprising to us, because the motivation from the behavioral people is that the higher levels are supposed to be scarcer. Things get even worse when we look at the predictions, because the level 2 agents, who are supposed to be the smart guys, end up with really low precision, which means they do something very similar to uniform randomizing, which isn't so smart after all. Even worse, if I look at this red line here, which is the precision of the level 1 guys, and compare it to the dotted red line here, which is the precision that the level 2 guys think that the level 1 guys have, they're incredibly different from each other. And worst of all, the level 2 guys are really sure about what the level 1 guy's precision ought to be. Right? This is a very, very concentrated distribution. All of its mass is right here, almost at 0. So what this is saying is the level 0 guy, the level 2 guys are not that smart. They do something close to randomizing, but not quite. The level 1 guys are pretty smart. They're really doing something that looks a lot like best response. But the level 2 guys are absolutely convinced that the level 1 guys are idiots and are uniformly best responding as though they were level 0 guys. So we end up with that makes the level 2 guys a lot like level 1 guys, because they're responding to uniform randomizers just like level 1 guys do, but just with a different precision. And so this whole thing is very messy and doesn't seem in any way really to justify the intuition that went into the model. It seems as though the model is sort of hacking in all of its parameters to say something different from what we really wanted it to say.
Are the level 2 guys getting better payoffs than the level 1 guys?
It's a good question. I have no idea. I mean, in the end, we're not really looking at these guys as though they're real guys, right? We're aggregating the whole thing to get a distribution that does a good job of predicting the data. And believing that there are this many level 2 guys who do this kind of thing is the thing that maximizes the probability of seeing the data that we saw. And that's the way to think about it.
Wait, so this implies that a good model would also just have a single type of guys who are responding to uniform?
No. If it had wanted to, it could have just set the probability of level 2 guys at 0 and said there was really only one type. And it's found that the probability that there's absolutely no level 2 guys is 0, right? It doesn't give any level 2 guys until we get up to here. So it thinks there actually have to be kind of a lot of level 2 guys, right? This distribution could have kind of looked like that, but it doesn't.
Yeah, but then I'm trying to understand. I mean, maybe you'll get.
So what it seems to be saying to us, I mean, it's a little bit. All you can do is kind of make theories about it, but it seems to us that what it's saying is, this isn't exactly at 0. So there is kind of a difference between believing that they're really at 0 and believing they're kind of close to 0, and that difference seems to matter. I mean, if you really zoom in, they're not right at 0. But it seems to be saying it's important to think about having 2 different kinds of precisions in the population. And essentially the levels get used to simulate those 2 precisions more than they're used to simulate actual levels in the way that was intended. But most of all, I just look at this and I think, oh, this is so not what I wanted to see. And all of these multiple modes mean they're probably also really complex. So I'm looking here at marginals, but these are all marginals on this posterior surface. So what I'm also seeing, and I have other evidence for it that I'm not showing you, that there are really interactions between these parameters, and that really not all kind of combinations of these things that these pictures show you are really equally likely. They get paired up in complicated ways. And so really this just tells me the whole story is very complicated.
I might be reading this wrong, but if the level 2 guys are acting like level 0 guys, and it looks like you got like a 50% chance of having 20% level 1 and about a 40% chance of 50% level 2, or sorry, 4%.
Okay.
If the level 2 guys are basically the level 0 guys, that sounds like what you're looking at is 80%.
The level 2 guys are not the level 0 guys. They're kind of a different kind of level 1 guys.
Okay.
In a sense, right? Because they're still best responding to something. Right? Their lambda here is not 0, so they really are thinking about some kind of best response. But let's not analyze this too much, because I want to get to the punchline before too many people have to leave. And I do have one more kind of more inspiring than this thing to say. So basically looking at this, we asked ourselves, we thought, boy, this is not telling us everything we want to know. And this to me really says QLK is not really the right model, because the ideas that went into the model are not getting justified by kind of what's coming out in the data. The data is kind of fighting the model in some sense, and it's doing well in the end, but not quite in the right way. So it made us ask, maybe we can change the model in a way by reparameterizing it that's going to give us something more reasonable. And this kind of goes in Lance's direction of thinking about different parameter spaces. So we essentially made a family of QLK-like models that differ in their parameters. So one thing we could change is what is the top level. So QLK says the top level is 2, but there's no reason why that should have to be true. We could consider top levels between 1 and, say, 7. And we could also consider this Poisson idea that we saw in cognitive hierarchy and just have a single parameter. The precisions, we could say every level has its own precision, as we saw here. Or we could say all the levels have to have the same precision. I bolded the thing that QLK does. But the precision beliefs, I could allow for this possibility that every level can have wrong beliefs about all the levels below it, but that seems complicated. It could also just be the case that everybody knows the precisions of the levels below them. And these population beliefs, we saw before there were two ways of having these beliefs. There's this level K thing where everybody believes everyone is just below them, or there's this cognitive hierarchy thing that believes that you know the true truncated distribution below yourself. So we basically looked at all of the different combinations of all of these ideas that led to 10 or fewer parameters. We didn't want to look at really ridiculous numbers of parameters, partly for numerical reasons, but we exhaustively explored the space of all combinations of these ideas with 10 or fewer parameters. And here's what we found. So this picture here, you can really see my dot. This picture here is showing you the likelihood of each one of these different models, where the x-axis shows the number of parameters in the model, and the y-axis is showing you this likelihood improvement that you saw before. And the black dot here is the original level K model, which I'm calling GI-QLK2 because it uses the level K beliefs, the general and inhomogeneous precisions, and a maximum level of 2. This red line is the Pareto frontier of performance as a function of number of parameters. So this is saying, this is the model that does the best among all models with its number of parameters or fewer. And this is everything above this is not statistically distinguishable from this one, which is why the Pareto frontier stops at that point. So this is all using a statistical significance test. And so what we found is 4 models that are on this Pareto frontier, depending on how many parameters you want. And the amazing thing is there's a really regular pattern to which things belong to this Pareto frontier. They're all AH-QCH models with different distributions over the number of levels. So they're all models that have accurate precisions and homogeneous precisions. So in other words, they all have just a single lambda for everybody, which everybody commonly knows. So all of this messing around with the lambdas just actually really doesn't seem to be a good idea. And then what this is basically saying is it is a good thing to think that there are more levels. So we can get improved performance as we have more levels. And surprising in the light of the behavioral game theory literature, it's good for us to go all the way up to 5 here, where really in the behavioral game theory literature, people have argued kind of for a long time that you only really want to go up to about 2. And here we see that continuing to increase it seems really to help. So here we have the Poisson model does well for having a small number of parameters, but it turns out the shape of this distribution really doesn't look like Poisson. So the last kind of technical thing I want to show you, here's this graph that I showed you before of the original QLK model. And let me contrast that with the QCH3 model, this one here, because it has a pretty small number of parameters and does better than the original one. So here's what it looks like for QCH3. And this is the kind of graph that I do want to see, because all of these distributions are unimodal. So unlike these awful step models that I had before, all of these are kind of nice, smooth CDFs that just have a single peak, which means the model is really doing much more what it was meant to be doing. So what I end up seeing now is that I end up with a precision which is kind of low but non-zero, and very definitely described by the data. See you, Lance. And I end up with these level proportions. The level proportions now look much cleaner than they did before, but the interesting thing is I still have a real spike at the level 2. And as we looked even higher into the 3, 4, and 5 models, we saw this pattern was robust. So what we really found was there's a lot of level 0 agents, not very many level 1 agents, and then a lot of 2, and then decaying numbers above 2. And as we go out into 5, that was kind of reliably true. And intuitively, that's why the Poisson model doesn't do very well, because it doesn't allow us to have a dip at 1, which really seems to be argued for by the data. So this seems to be just a place where the intuition in the literature is wrong, that the higher level models should be scarcer. Indeed, it seems they should be scarcer, but there should be a spike at 2. But overall, I really like this story because what it says is, here's a general model family that seems to really work. It can have as few as 2 parameters, and you can add parameters only to control really one thing, which is the shape of this distribution. And generally speaking, I think the shape should have kind of these 2 bumps. We can probably find a single parameter story that would do a good job of describing those 2 bumps. And then we could probably end up down with a 2-parameter model that would do a good job of describing all of this data. So it really does seem here that we can improve performance by limiting the number of parameters, as long as we use those parameters to describe something that really is present in our data. And so here's kind of the final story of how all of these models do on this Combo 9 data set, just to kind of summarize everything. So here are the different Nash models. This is the non-deterministic Nash model that I could never really use. Here are the 2 strategic reasoning models and the QRE model. And then here are the different variants of QLK. So this is the original QLK model. This is the Poisson one. And these are our 3 variations that use 3, 4, and 5 levels. And so I think in the end, this AHQCH3 model is really kind of a nicer model to think about than this QCH model in literature, particularly a QLK model in literature, particularly because all of these lambdas were really very hard to think about, all of these wrong beliefs, and it really turns out that it just doesn't help anything to have that flexibility in the model. So that's my story. So in the end, I've compared the predictive performance of all these different models, and I've shown you the results of this Bayesian sensitivity analysis, and in the end, kind of used that to derive a new model that both fits the data better and is, I think, easier to think about. So happy to take some more questions, and thanks for your attention. Sure, yeah, I'm around.
Yeah. Oh, cool. Great. Yeah, very nice.
I don't have a meeting, but I'm not